Hello and welcome all my dear student of first year BSc class. This is the last lecture of first chapter Fundamental of Thermodynamics, and in this lecture we are going to solve some remaining important problems, because few of the problems we already studied in previous lecture. So in this lecture we are going to solve a problem number 4. A problem is very simple. A definite mass of a perfect gas is compressed adiabatically to half its original volume. Determine the resultant pressure if the initial pressure was 1 atmosphere. Okay. What is the problem? A definite mass of a perfect gas and this gas is compressed adiabatically till to half its original volume, original or initial volume. Okay. Determine. Here what we have to determine? Determine the resultant pressure. Pressure if initial pressure was 1 atmosphere, and here given value of gamma is 1.4 and 2 raised to 1.4 is equal to 1.64, sorry 2.64. Okay. Read the problem carefully. A definite mass of a perfect gas is compressed adiabatically to half its original volume. Determine the resultant pressure of the gas if the initial pressure was 1 atmospheric pressure. So, in order to solve this problem, what is the given? So, solution given. Here which things are given? V1 and V2. V1 is equal to V and V2 is 1/2 V or V2 by 2. Also value of gamma is given 1.4. Okay. Remember that change is adiabatic and we are having the value of V1 and V2, and we have to find the pressure and we have to find the resultant pressure. When change is adiabatic or when process is adiabatic, then relation between pressure and volume P1 V1 raised to gamma is equal to P2 V2 raised to gamma. This is the adiabatic relation between pressure and volume in initial state, and this is the relation between pressure and volume in final state. Okay. Now rearrange this equation. P2, because we have to calculate the resultant pressure, P1 in bracket V1 upon V2 bracket raised to gamma. What is the value of P1? 1 atmosphere. Then what is value of V1? V upon 2V. Correct? Sorry. Final value V by 2 raised to gamma. Gamma is also given 1.4. We cancel and we have 1 into 2, because 1 upon 1 by 2 is nothing but 2 raised to 1 by 4. this value of 2 raised to 1 by 4 is already given, and hence P2 resultant pressure is 2.64 atmosphere. This is the final answer of a given question. See here, how simple problem is this? You have to only read the problem carefully and keep in your mind that change is adiabatic, and for adiabatic change we already studied this relation. Okay. Now second problem, next problem. Now a certain mass of a gas, next problem. A certain mass of a gas. Wording are changed. A certain mass of a gas at certain mass of a gas at 0 degree Celsius. At 0 degree Celsius is expanded adiabatically to its 3 times expanded. Now we know that in expansion volume is goes on increasing, expanded to 3 times to its original volume. Original or initial volume. What it? Under adiabatic condition. Calculate the result, calculate the resulting pressure and temperature, and here also value of gamma is 1.4 is given. Read the problem carefully. See here, you have to keep it in your mind that the change is adiabatic change. Here which things are given? Volume and temperature, initial temperature and initial and final volume are given. Here we want to find out the final pressure and final temperature. So solution of the problem is very simple. Solution given. Which things are given? First of all, here V1 is equal to V and V2 is equal to 3 times, that is 3V. Then temperature is also given. T1 is 0 degree Celsius, converted into 273 Kelvin. Okay, and value of gamma is also given, and gamma is equal to 1.4. This one. Okay, for adiabatic change, because condition is adiabatic condition. Adiabatic change, relation between temperature and volume, T1 V1 raised to gamma minus 1 is equal to T2 V2 raised to gamma minus 1. T1 V1 raised to gamma minus 1 is the adiabatic relation between, or is the relation between temperature and volume when change is adiabatic or process is adiabatic in initial state, and T2 V2 be the adiabatic relation between temperature and volume in final state. So rearrange this equation. We have T2, here we are having value T1, V1 and V2. So we want to find out the resultant temperature. T2 is equal to T1 in bracket V1 upon V2 raised to gamma minus 1. Very simple way. Now substitute the value of T1 273, then V1 upon V2 is V upon 3V raised to 1.4 minus 1. Solve this 273 into 1 by 3 into 0.4. You can solve it by using log table or by simply calculator. you will have the answer like this, 176 Kelvin. Very simple. This is the resultant temperature. Now in order to find the resultant pressure, when again change is adiabatic, then P1 V1 raised to gamma is equal to P2 V2 raised to gamma. We have P2, we want to calculate P2, then P1 into V1 upon V2 raised to gamma. What is the value of P1? P1 is initial value, P1 is equal to 1 atmospheric pressure. See here, original mass of perfect gas. Okay. So, substitute the value of here, P1 is equal to 1, V1 is equal to 1 upon 3 V2, or V cancel, V get cancel, raised to m 1.4. So, 0.3 into raised to 1.4. Solve this, you will get 0.215 atmospheric pressure. This is the resultant pressure. In this way, you can calculate the resultant temperature and pressure. Okay. Then here only few words are missing. Calculate the resulting pressure and temperature if the initial pressure was 1 atmosphere. Here is the initial pressure was 1 atmosphere. Okay. Now next problem. Problem number 7. Next problem. This is very important problem. A motor car tires. Problem number 6. A motor car tire has a pressure 2 atmospheric pressure, 280 MPa at a room temperature. Okay. Room temperature of 27 degrees Celsius. If the tire is suddenly burst, find the resulting pressure, or find the resulting temperature. Here also gamma for year is equal to 1.4 is given here. So look toward the problem. Problem is simple. A motor car tire has a pressure 2 atmospheric at room temperature 27 degrees Celsius. So given thing, solution given here P1, or we can say that pressure before burst is P1. This is 2 atmospheric pressure. Okay. Now temperature before burst is equal to T1, and this is given 27 degrees Celsius, which is nothing but 273 Kelvin. Okay, 73 plus 27, 300 Kelvin. Now pressure after burst, that is P2, is 1 atmosphere, 180 MPa. atmosphere pressure. This is the given thing. See here, a motor car tire has a pressure 2 atmosphere at a room temperature, and if the tire is suddenly burst, find the resulting temperature. Okay. See here. For adiabatic, the change is adiabatic change. When burst, this change is sudden change. At that time, P1 and T1 raised to gamma and P1 raised to gamma minus 1. This is the relation between pressure and volume, pressure and temperature when change is adiabatic change in initial state, and P2 raised to gamma minus 1 upon T2 raised to gamma is the relation between pressure and temperature in final state when the process is adiabatic. Or simply you can write T2 upon T1, arrange this is to gamma, okay, and okay, P2 upon P1 raised to gamma minus 1. Put up the value of T1, T2 upon 300 is the value of T1, 1.4. Okay, then pressure 1 atmospheric upon P1 2 atmospheric, that is 1/2, 1.4, which is the value of gamma minus 1. Okay, when you rearrange and solve it, you will get value of T2 is equal to 246.1 Kelvin. This is the value Kelvin, and 246.1 minus 273 is equal to minus 26.9 degrees Celsius. This is the final temperature when tire is suddenly burst. Okay. Now next problem number 7. You should have the habit to solve the problem, but before solving the problem, you have to read the problem carefully. See here, we are going to see another problem. The temperature of 4 gram of air. Next problem number 7. The temperature of 4 gram air. Temperature of 4 gram of air is raised from 0 degree Celsius to 0 degree Celsius to 1 degree Celsius at constant volume. The temperature of 4 gram of air is raised from 0 degree Celsius to 1 degree Celsius at constant volume. Compute or calculate the rise or increase in its internal energy. Okay, here value of specific heat is given. Specific heat for air at constant volume that is CV is given, and this is nothing but 0.172. Okay, and calorie per gram per degree Celsius. Okay, and value of J is also given 1.8 joule per calorie. These two things are given. So read the problem carefully, collect the data. So here the temperature of 4 gram of air is raised. Temperature of 4 gram of air is raised from 1 degree Celsius, 0 degree Celsius to 1 degree Celsius at constant volume. Calculate or compute the increase in its internal energy. Specific heat of air at constant volume, that is CV, is given. Mechanical equivalent of heat is also given. So in order to coin this problem, solution from first law of thermodynamics, the change in its interval, we know that. This is the significance of first law of thermodynamics. First law of thermodynamics introduces the concept of internal energy, and first law of thermodynamics provide the method to calculate the change in internal energy. So du is equal to dq minus dw, because dq is equal to du plus dw. This is the statement of first law of thermodynamics. We just rearrange it and we will get du is equal to dq minus dw. Here volume is constant. Here V is equal to constant. When volume is constant, then obviously change in volume is equal to 0. Change in volume is 0. Hence dw is equal to P dV. Okay. This is also 0. See here, if there is no change in volume, if the volume remains constant, then change in volume is 0. And when change in volume is 0, then change in volume into pressure 0. Therefore work done is also 0. As dV is equal to 0, P dV is equal to 0, and work done is 0. Therefore, see here, du is equal to dq. Okay, du is equal to dq, because this is equal to 0. Why this is 0? At constant volume change in volume is 0, and when change in volume is 0, then work done is 0. Therefore d is equal to dq, and this is nothing but mass into specific heat into rise in temperature. So mass 4 gram into specific heat 0.172, this one, and rise in temperature 1 minus 0 into 1. Okay. So simply make the calculation of 4 into 4 and 0.172, and this is nothing but 0.688 calorie. Okay, but here mechanical equivalent of heat is given, and we know that W is equal to JH. So 1.8 into 0.688, you will get 2.88 joule. This is the work done in joule. This is calorie. In this way you can calculate or compute the increase in internal energy, because internal energy is like this. Okay. Now see the next problem or last problem. Okay. Before, see here, what is the change in internal energy? Again, next problem is on internal energy. Problem number 8. What is the change in internal energy? What is the change in the internal energy? What is the change in internal energy per gram? Per gram of air AIR. If 12 gram of air is heated from two temperatures given 0 degree Celsius to 5 degree Celsius. Okay, at constant volume. At constant volume. Okay, constant volume. By adding 120 calories of heat. See the problem once again. Read the problem carefully. What is the change in the internal energy per gram of air if 12 gram of air is heated from 0 degree Celsius to 5 degree Celsius at constant volume by adding 120 calories. Okay. Now, again here, the solution is again depend on first law of thermodynamics, because first law of thermodynamics provides the method to calculate the change in internal energy. So, solution from first law of thermodynamics, the change in internal energy of a system is given by du is equal to dq minus dw. Okay. Again, at constant volume, that is V is equal to constant, and when V is equal to constant, the change in volume is constant, change in volume is 0, and when change in volume is 0, then work done dw is equal to P dV, that is P into 0 is equal to 0, work done is also 0, and simply du is equal to dq, and value dq is nothing but 120 calories. 120 calories. Okay. Therefore, the change in internal energy per gram of air, change in internal energy per gram, that is du, change in internal energy per gram, 12 grams are there, is equal to 120 upon 10 is equal to 10 calories per gram is the answer of this problem. Okay. Now we are going to see the last problem of this chapter. Last problem. Calculate the work done. Calculate the work done when 1 liter of monoatomic perfect gas at NTP is compressed adiabatically to half its original volume. Solution. I am again going to read the problem, or I am again going to tell what is the problem. Calculate the work done. What we have to do? Here in this problem we have to calculate the work done. The given data is like when 1 liter of monoatomic perfect gas at NTP is compressed adiabatically to half its original value. That is not given. V1 and V2. What I say? Calculate the work done when 1 liter of monoatomic, 1 liter, V1 is equal to 1 liter. 1 liter is nothing but 10 raised to 3 cubic centimeter. Cubic centimeter. That means 10 raised to minus 3 cubic meter. Okay. We convert this because in problem 1 liter of a monoatomic perfect gas is there, and that gas is compressed at NTP adiabatically to half its original value. So, half 0.5 liter, half of 1 liter is 0.5 liter, again 0.5 into 10 raised to minus 3 cubic meter, or simply 5 into 10 raised to minus 4 cubic meter. This is the value of V1 and V2. For adiabatic compression, we have work done. For adiabatic compression, 1 upon 1 minus gamma upon 1 upon V2 raised to gamma minus 1 minus 1 upon V1 raised to gamma minus 1. Okay. So substitute here again, gamma is given 1.67 in this problem. So 1 upon 1 minus 1.67, again here V2 is given, this V2, that is 1 upon 5 into 10 raised to minus 4 and 1 0 minus that is 0.67, because 1.67 minus 1, value of gamma is here, minus 1 upon V1, so 10 raised to minus 3, 0.67. We simply put the value of V2 and V1 in the here and gamma. Solve this. When you solve this using calculator or log table, you will get the answer like minus 90.3 joule. Here negative sign is there. Negative sign indicate that work is done on the gas. Work is done on the gas, not by the gas. Hence, work done on the gas is 90.3 joule, because work done is never negative. Just when it is positive, it is work done by the gas, and when negative, then work is done on the gas. Work is done by the gas during expansion, and work is done on the gas during compression. And when compression of the gas takes place, obviously volume goes on decreasing. Okay, and hence work done is negative. Okay, are you got it? Okay. In this way, I will try to solve most of the problems in the chapter, but due to lack of time, it is not possible to take large quantity of problems. So, when I will provide PDF notes to you on our WhatsApp group, at that time, I will provide you the solved problem. Okay. Till then, we shall stop here. Have a good day. Thank you.